Yeah, now it's finally time that we talk about multilayer perceptrons. So what is a multilayer perceptron? So multilayer perceptrons are fully connected feed-forward neural networks with one or more hidden layers. So what does the fully connected mean here? So fully connected means that if you have a given layer, each unit in that layer is connected to all the other units in the next layer. So for instance, if you have a layer, let's say like this, an input layer, and then you have another layer, let's say with only one unit, then each input is connected to that one. It's actually similar to logistic regression in that way. So in a logistic regression context, we also had everything in the input layer being connected to the next layer. Or if we had multiple outputs, we had also this setup. And this is actually similar to a multilayer perceptron, except where in softmax regression, we had an input and an output layer. Let's make maybe one more here. Now what we have is we have a hidden layer, so that means there is another output layer, for example, like that. So instead of being softmax regression, we have now a multilayer perceptron, and in the middle here we have a hidden layer, and now this one becomes our new output layer. So again, everything is connected here. So that's why it's called fully connected. And the main difference between a multilayer perceptron and softmax regression is that we have this hidden layer here. Also, we use a learning algorithm called backpropagation, which is actually just gradient descent using the chain rule. It's essentially very similar to what we have done in the last lecture when we talked about softmax regression, except again that we have now a hidden layer. All right, so another term here is feed forward. So feed forward refers to the fact that we go into one direction from left to right in this particular drawing, but essentially from the input to the output. So that means feed forward. Later we will see other networks that are not feed forward. For example, there are recurrent neural networks where we have a recurrent layer where you go essentially backwards. There's a time dimension. I should also say not all networks are fully connected. So later in this course we will also see convolutional networks which are not fully connected. All right, but I'm way ahead of my slides here. I just see I explained almost everything already because I made actually some nice figures. So let's take a look at these figures. So here I'm showing you a multilayer perceptron with two hidden layers. So we have on the left hand side the input layer, then a hidden layer, another hidden layer, and then the output layer. And because we only have one output unit, similar to logistic regression and different from softmax regression, this one would be a binary classification problem. And so for the output, we can actually use a sigmoid function similar to logistic regression. Other than that, there is nothing really new here. I mean, this is just like softmax regression, except that we have now these hidden layers, right? So in that way, there's actually not that much to explain because, we have also the same way these weights connecting each unit between the layers. And when we then compute the partial derivatives for, training this network, we can also use the chain rule, the multivariable chain rule. So for instance, if we would want to compute the partial derivative of this loss function, or the loss here, with respect to one of the weights, then we would also use the chain rule to go backwards, and then the multivariable chain rule to combine the output from different units. So what I mean is, if we have the output here, then we go backward. So we are interested in this weight W11, just as an example. So I'm just highlighting all the paths. So there's one path that goes here, you can see it here, right? And the other path is this one here. So in purple, what I'm showing you is this one here at the top. And then in here, for the multivariable chain rule, this is this path here. So there are two paths actually. And that is actually it. That's how we would train or update this weight. Notice that there are, of course, multiple weights, actually multiple weight layers. So here we have, for example, the weight in the second layer. We will train those also, of course. So in this case, yeah, the rule would be a little bit different. So in this case, let me just take a look. We have, let me write this down maybe. So we have the partial derivative with respect to this one, which should be loss with respect to the output, and then the output with respect to A1, 2, right? And then A1, 2 with respect to, we were saying 1, 1, 2. So in this way, you can see this path here is actually, let's see, this part here is actually shared with this path here, right? So actually you can reuse, if you compute this one first, you can reuse this part in order to compute this part for backpropagating further. So also when you implement this in practice, yeah, there are some tricks to avoid recomputing things or gradients here. But fundamentally, that's the same concept that applied to softmax regression. So here, really what I wanted to say, there's nothing new really. Yeah, here's a figure we looked at earlier in this course, these different types of learning algorithms. And this algorithm that we use for training the weights in the multilayer perceptron that I just showed you, based on the partial derivatives or gradients, that's called backpropagation. That's one type of learning, and yeah, it remains still to as the most precise learning algorithm. So there was this paper in 2020 where the authors proposed an alternative algorithm that may be more similar to what's going on in the brain, but the backpropagation algorithm is still the most efficient one for training neural networks. So now let's talk a little bit about the nomenclature. So here that's the same figure as before, and notice that I'm using these round brackets or parentheses here. So before, when we had something like this with the square brackets, this was usually referring to the first activation for the ith training example. Here, the round parentheses, they don't, or this doesn't mean this is the first training example. This really means here the first hidden layer. So the round braces here, the parentheses refer to the hidden layer index. So here we have two hidden layers. So you can see this is the first hidden layer, and then here we have the second hidden layer. And I could also, instead of writing output here, I could also write activation with a parentheses here 3, because the way the output is computed if we use the sigmoid function is the same way as these activations are computed. So for example, if you have one activation here, let's say the one in the first hidden layer, this is really computed as the activation based on, let's say, some net input z, where z is computed as the net input here. So I'm not showing, I should say, I'm not showing the biases. So there should also be a bias for each activation. So I was not drawing it because the figure was already so crowded. See, it's a little bit messy, so let me remove this again. But there should be a bias also for each activation. Okay. And this is for this unit here, but now if we take a look at this one, so for this one we would compute it the same way, except now that we, instead of, so we still have z, so let's just use the same letter z, but z is now not, of course, involving the axis directly. It's based on the previous layer activations. So in this case, you can think of it as the previous layer activations. So W transpose plus b. I'm not using indices here for the weights, but this would be, of course, these would be the weights from the previous layers respectively. So here I was just focusing on what the inputs are. For this second one here, we have the activations of the previous layer, which act as the inputs to that layer, if that makes sense. So for this layer, we have the axis as input, and for this layer, we have the activations from the previous layer's input. Actually, the main point here I also wanted to make is how we count the layers. So it's quite common, I've seen that a couple of times, referring to the input layer as the first layer in the network. Then the first hidden layer is the layer number 2, the second hidden layer is the layer number 3, and the output layer would be layer number 4. We could do that, but then it would be a little bit weird when we talk about logistic regression, because then logistic regression is a 2-layer network, which is kind of weird, because usually you think, or we think of logistic regression as a single layer neural network. So what I mean is, if we count like that, if we then remove these hidden layers, we have an input layer and an output layer, like in logistic regression. This would be a 2-layer network, and that is a little bit weird. So in this way, we usually use the indices a little bit differently. So this is like the input layer is sometimes also called the 0th layer, or just input layer, and the first hidden layer is the first layer, the second hidden layer is the second layer, and the output layer in this case would be the 3rd layer. So that's a little bit more intuitive if we think of logistic regression as single layer neural networks. So yeah, like I said, we can use the sigmoid, the logistic sigmoid function here everywhere as activation function. So then it would be really like logistic regression, except that we have these hidden layers in between. But the loss function could also be the negative log likelihood that we talked about, or we can also call it binary cross entropy, which is here equivalent to the negative log likelihood. Actually, for classification in neural networks, that's also the most common loss function. And that is, again, why we spend so much time on logistic regression and softmax regression, because fundamentally things are very similar. Yeah, and also like in softmax regression, if we have multiple output units, instead of using sigmoid functions here, we can use the softmax function. But yeah, I don't have to explain how softmax works again. If you forgot how softmax works, then yeah, we have lecture 8. So the nice thing about lecture recordings is that you can revisit lecture 8. Yeah, now an interesting question is this really deep learning? I mean, multilayer perceptrons have been around maybe for 50 years already. So is this really deep learning if we have the same multilayer perceptron that has been around for such a long time? And how is it different from a neural network? What's the difference? Yeah, now the interesting question is this really deep learning? I mean, multilayer perceptrons have been around, I would say, for 50 years approximately. So yeah, can we really call that multilayer perceptron we just saw deep learning? So according to the recent trends, when I look at recent papers, it's more and more common to call these multilayer perceptrons deep learning. So here's just a figure I saw recently in a paper. I don't want to reference this paper in this case because I think, I don't want to blame anyone for calling this deep learning, so I don't want to call out certain people here. But here in this paper I read, for example, there was this figure of a multilayer perceptron where there were only 10 inputs, very small numbers of hidden units, and then one output. So output unit. So here they called it deep learning and essentially proposed this deep survival model. So like I said, it's more and more common to call these multilayer perceptrons deep learning. Traditionally, when the term deep learning was coined, like I mentioned in the introductory lectures, it usually referred to the feature learning by using certain tricks that are a little bit beyond the regular multilayer perceptrons, where we had certain algorithmic improvements of neural networks that make the learning more efficient. But nowadays, a multilayer perceptron, I would say, is already deep learning in a sense. Another very important point is that now in a multilayer perceptron, the loss is not convex anymore. So in linear regression, Adeline, logistic regression, and softmax regression, we had convex loss functions. So for example, for linear regression, if we recap how the loss looked like, let's say with respect to one weight, because it's easier to draw, it would be something like this bowl shape here, where let's say we start with an arbitrary weight value here, or let's say we start with weight 0 here. So the loss would be, let's say, very high when we start, and then we go down with gradient descent till we reach this global minimum. Now in the case of multilayer perceptrons, it's not that simple anymore. We don't have such a nice convex loss function where there's only a path downward to the global minimum. So in fact, these are highly non-convex loss surfaces now. So I found a nice paper that is about visualizing the loss landscapes of neural networks. So here, this is for, or if you have or consider two weights in a neural network. So if we have, let's say, W1 and W2, let's say W1, W2, 1, and let's say in the first hidden layer, because there are many weights in the neural network. But you can see that this loss is highly complex. There are many local minima going on here. And here I think that should be the global minimum. So if we find the values of the weights that we are here at this point for this loss. So here the loss value, let's say the higher, so this is the maximum, the higher, the larger the loss, and the lower the loss. So if we are at this global minimum here, then we would have minimized the loss function with respect to the weights. However, depending on what our starting weights are, so typically in the context of neural network training, we start with small random weights. So one reason is why we start with small random weights is that we want to try different configurations. So for example, if we have a configuration of weights, we may start here, we could start here or here, depending on what our initial weights are. And it's not uncommon that we get stuck in a local minimum. So we reach one of these local minima and then the algorithm gets stuck. In practice, it's actually almost, I would say, impossible to find the global minimum. So you never know whether you reach the global minimum. Usually, common knowledge is that you will end up in some of the local minima, and it's not uncommon because of that to start the neural network training multiple times with different random seeds. So sometimes you have a better random seed for a given network than other times. So sometimes you will notice that you will have a better performance just by changing the random seed. So in papers, it's thus also not uncommon to, let's say, run a network training 5 or 10 times. Then take maybe the best 3 runs and then average over them and report the standard deviation and things like that. So we deal now with this highly non-convex loss surface, and in the next couple of lectures we will also talk about tricks for choosing learning rates, choosing initial weights, and choosing optimization algorithms that can help jumping out of these local minima once we get stuck. So there are certain tricks and improvements to make the learning more efficient compared to the traditional stochastic gradient descent version. And beyond choosing good starting weights and good learning rates and good optimizers, it's also very important to choose good activation functions and combinations of activation and loss functions. So here I just want to illustrate a problem with certain activation and loss functions. And in the next videos, we will talk about, let's say, alternative activation functions, which are nowadays a little bit better for training multilayer perceptrons. So here for this example, consider we have a logistic sigmoid activation and a mean squared error function, loss function. So one problem we may encounter is that we may end up with very flat gradients. And especially then if the output is very wrong. But if you think about it, if we make a very wrong prediction, we want to actually have large gradients because then we can update the weights more. If the gradients are very flat, then there's almost zero weight update, and then we can't fix our problem of the wrong prediction. So recall how the logistic sigmoid function looks like. So if we have a logistic sigmoid function like this with a net input, then recall it was like this S-shaped function. And let's say the true class label is 1, but we return a very low probability, like let's say, the probability, class membership probability is 0.001 or something like that, right? So if you look at this, a low very negative net input and a low probability will result, of course, in these very flat gradients. So if you then look at the derivative of the loss function with respect to the weights, so here we have the derivative of the mean squared error loss with respect, let's say, to the activation. Let's call that just sigma here. And then this is partial derivative of sigma with respect to the net input. And then the last term, remember, is the derivative of the net input with respect to the weight. So here we are again using the chain rule, but if we have the derivative of the sigmoid here, and now C combined with the MSE, it doesn't cancel so nicely. So when we had the binary cross entropy and the sigmoid activation, things canceled nicely, that we ended up with this nice learning rule, right? So we had this nice learning rule where we didn't have this problem. But if we use, for example, a mean squared error function combined with these sigmoid activations, we end up with this derivative here that has the problem that it has this term itself. Now, if this term is very small, so if we make a very wrong prediction, let's say 0.001, maybe even smaller, let's say 0.000001, then we multiply this very small value with all the other values here, so the whole derivative will become very low or very small, and then we will almost update our weights by nothing. So in that way we can't fix this wrong prediction. So it's kind of also important to think a little bit about what types of activation functions we combine with which types of loss functions. Here's another point I made, but here this point is really, I was just saying, if you have a multi-layer network, of course you would use a softmax activation if you have mutually exclusive classes instead of sigmoid activations in the last layer, but the same problem would still exist, so that doesn't really solve our problem. I just wanted to add this as a small note. Alright, so the next video I will show you then different types of activation functions that are a little bit better than logistic sigmoid functions in a multi-layer perceptron. But as an ungraded homework exercise or Piazza discussion point, I wanted you to think about a little aspect about multi-layer networks. So I have a question here for you. What happens if we initialize the multi-layer perceptron to all 0 weights? So before I mentioned we use different small random weights to escape these local minima, or just to have different starting points, so we may end up finding better local minima if we run this multiple times with different random starting weights. But now consider the case where we set all the weights to 0. It's just unrelated to these local minima. I just wonder if you can think of what happens if we choose all the same values for the weights. Because you may think, okay, why do we use small random values? Why don't we use just small numbers and have the same number for each weight, or have all the weights at 0? So that's maybe something to think about. And then in the next video we will talk about nonlinear activation functions.